What's up everybody, and welcome to a new series. And in this series we're gonna cover how the naive Bayes algorithm works. So let's get straight into it. Namely, as the name implies, naive Bayes is based on Bayes' theorem, and the formula for that looks like this. However, I'm actually going to explain how the algorithm works without actually using this formula here. And that's because this way I think one can get a more intuitive understanding of how the algorithm works. And then once we have that, we will go back to Bayes' theorem and check or see that we've actually done the calculations according to this formula. Okay, so now then to explain how the algorithm works, we're gonna need some data, and we're gonna use the Titanic data set. So this is a data set that contains information about the passengers of the Titanic accident. So each row that we have here is one specific passenger, and in total we have 891 passengers. And the features that we have are the sex of the passenger, so if the passenger is male or female. Then we have the passenger class, so if the person then traveled in the first, second or third class. Then we have the age group, so if the passenger is a child, teenager, adult, or if the age is unknown. Then we have here the feature embarked, so this is where the passenger got on board. So S stands for Southampton, C for Cherbourg, and Q for Queenstown. And then here we have the number of siblings and spouses that the passenger traveled with. And then here the last feature is the number of parents or children that the passenger traveled with. And then here in the last column, we have our label. So this is called survived. So this tells us whether the particular passenger survived or not. So if it's 0, then the passenger did not survive. If it is 1, then the passenger did survive. And this data set here I got from Kaggle. However, I made some changes to the data set. Namely, first of all, I didn't use all of the features that were available on the dataset on Kaggle. And then the second change that I made is this age group feature here. Originally in the dataset, this was just called age, and there was the age given in years. And why I made this particular change, we will then see in the next video of the series. Okay, so then, so if you want to check out the data yourself, then you can either go to Kaggle and download it and then prepare it yourself, or you can go to the corresponding blog post for this video and then there get the data that I've already prepared. And I will put the links to those both into the video description. Okay, so this is then our train data. So then obviously we also need some testing data, and here the survived column is obviously missing because that's what we want to predict. So for those 4 test passengers here, we want to predict whether they survived or whether they did not survive. Therefore, let's look at this, or let's have a closer look at this first passenger here. So this is a male who travels in third class. The age is unknown. He embarked at Southampton, and he traveled with 0 siblings or spouses and 0 parents or children. And the question that we now want to answer is, given that the passenger has these particular values here, did that passenger survive or did that passenger not survive? And so now let's think about how we could go about answering that question. Namely, the probably simplest approach is to just look at all the passengers in our training data set that have the exact same values as this test passenger 1 here. So if we do that, then we're only looking at males that travel in third class, where the age is unknown, and so on. And here then we can see that there are 42 passengers in our training data. And then we simply check how many of those survived and how many of those didn't survive, and whatever happened more often, that's going to be our prediction for this passenger here. So let's do that. So if we then check how many survived, then we can see that 38 out of those 42 did not survive and only 4 survived. So let's also see what that looks like in percentages. So you can see then that 90% of the passengers that have the exact same combination of values as test passenger 1 did not survive. So therefore, obviously, then our prediction would be that this passenger also didn't survive, simply because it's much more likely. So let's see if that's really the case. And here, indeed, this passenger did not survive. So our prediction here was correct. So now let's do this the same thing for the second passenger here. And here then we can see that there are in total 25 passengers that have the same combination of values as test passenger 2. And here then 88% of those survived. So obviously then we would predict that this passenger here survived. So let's see if that's the case. And indeed, our prediction was correct again. So now let's do the same thing for this third passenger here. And here then something strange happens, namely we have 0 examples in our training data that have the exact same values as this test passenger 3. So now obviously we have a problem, because here we have 2 zeros, so we don't know what our prediction for this passengers should be. So what do we do now? Well, maybe this is just an exception, and if it is, then we can think about what we should do about that later on. And if it's not an exception, then we have a problem with our current lookup approach here. So let's have a look at this fourth test passenger. And here again, there are 0 passengers in our training data. So having 0 examples of a specific combination of values in our training data doesn't seem to be just an exception. So let's now think about why this might happen. Therefore, let's recap what happened so far. Namely, for those first 2 passengers here. So for the first 2 specific combination of values, we had examples in our training data, namely 42 and 25. And for those last 2 specific combination of values, we didn't have any examples in our training data. So now, therefore, let's think about how many combination of values there actually are in total. Therefore, to see how we can calculate that, let's first just look at the feature sex and passenger class. So the sex can take on values male and female, and passenger class can take on values 1, 2, and 3. So now let's write out all the possible combinations that we can create out of those 2 features. And then here we can see that we could have a male that travels in first, second, or third class, or we can have a female that travels in first, second, or third class. So in total, we could have 6 possible different combinations out of those 2 features. So now, obviously, then when we want to determine the number of total possible combinations for all the features in our data set, then obviously then writing out all the possible combinations is not really practical, but luckily we don't have to do that, because we can also calculate this number. And therefore we simply have to know how many distinct values each feature has. So let's do that here for sex and passenger class. So here we have 2 different values, or 2 distinct values, and here for the passenger class we have 3. So then if we simply multiply those numbers together, so 2 times 3, then we also get the result that there are 6 possible combinations. So now then to calculate the number of possible combinations for all those features, we now need to know how many distinct values each feature has. And here I've created a table for that. So as you can see, sex and passenger class we have 2 and 3, and then age group we have 4 distinct values, embarked 3, and siblings and spouses and parents and children both have 7 distinct values. So now we simply need to multiply those numbers here, and then if we do that, then we can see that we have here 3,528 possible combinations that we could create out of those 2 features, out of all of those features. And this is exactly where the problem lies, namely the number of total possible combinations is much bigger than the number of examples that we actually have in our training data. So therefore then it's obviously the case that there will be a lot of combinations for which we don't have any examples in our training data. And here you also have to keep in mind that these 891 passengers here, they don't represent 891 different combinations. Because as we've seen, for example, before here test passenger 1, this combination we had 42 times in our trained data. So let's write out how many actual different combinations we have in our trained data. So if you do that, then we can see there are only 199 different combinations. So the number of possible combinations is actually way bigger than the number of combinations that we have in our trained data. So then the fact that we have 0 examples for a specific combination in our trained data is actually not an exception, but it is rather the rule. And this is basically the case for any data set, not just this Titanic data set. And that's because the number of possible combinations grows exponentially with the number of features that we have in the data. And that's because we always have to multiply the number of distinct values. So it will be basically always be the case that the number of possible combinations here is generally much bigger than the number of examples that you will have in the data set. So what this now means is that we can't make use of this lookup approach here. So the question then is, what do we do now? Well, we might not have enough data to make use of this lookup approach here, but we do have some data and we can actually use that to estimate those numbers here. To be more precise, what we can do is we can look at all the non-survivors in our trained data and then estimate how many of those we would expect to have a certain combination of values. And then we look also at all the survivors in our training data and then estimate how many of those we would expect to have the same combination. So therefore now, let's actually write out how many survivors and non-survivors there actually are in this data set here. So if we do that, then we can see that there are 549 non-survivors and 342 survivors. So what we now want to do is we want to estimate how many of those 549 non-survivors we would expect to have a certain combination of values. For example, the combination of values from test passenger free, for which we, as we have seen, we actually have 0 examples in our training data. And then we do the same thing for the survivors. So we estimate how many of those 342 survivors would we expect to have the same combination of values as test passenger free. And then again, we have here 2 numbers, and whichever of those numbers is higher, that's going to be our prediction for this test passenger here. So that's the general idea of what we want to do now, but how do we actually implement that? Well, the main problem of our lookup approach here is that we sort of say consider all those features in our data set at once. And because of that, then the number of possible combination grows exponentially, and therefore then we simply won't have enough data. However, if we look at those features individually, then we actually do have enough data to at least find general patterns about non-survivors and survivors. And by general pattern, I mean how the values of a feature are distributed. So for example, if we look at feature sex, then what a general pattern would be to determine how many of the non-survivors are male and female and how many of the survivors are male and female. So that's what I mean by a general pattern. And then once we have those general patterns for each individual feature, we can say, so to say, put them back together to estimate how many of the non-survivors and survivors we would expect to have a certain combination of features. And this probably now sounded more complicated than it actually is. So let's see how we actually implement that. And then I think it will be pretty straightforward what we do here. So let's now start with estimating how many of those 549 non-survivors we would expect to have the same combination of values as test passenger free here. And therefore, as just said, we need the general patterns with respect to each individual feature. So let's start with the feature sex here. So if we check that out, then we can see that there are 81 female passengers out of those 549 non-survivors and 468 are male. So expressed in percentages, that means 15% of the non-survivors are female and 85% are male. So that's the first feature. So now let's do the second one. So the passenger class. So here we can then see that there are that 15% of the non-survivors travel in the first class, 18 in the second, and 68 in the third class. And here, if those numbers don't match up, that's just because of rounding errors. And now, since we actually don't have any more space here on this slide, let's not consider the remaining features for now. And this actually won't change anything about the explanation how naive Bayes works. Okay, so now we have all the patterns, all the general patterns that we need. So now let's estimate how many of those 549 non-survivors we would expect to have the same combination as test passenger 3. So how many of those we would expect to be female and to travel in first class. So now let's think about how we could do that. Well, we know that 15% of the non-survivors are female, and we also know that 15% travel in the first class. So how many of the non-survivors would we expect to have both of these values? Well, the straightforward thing to do is to simply multiply those two percentages together and then multiply that with 549. So you can think of it like this. So let's say we have here 10 squares, and let's say that we can randomly assign 40% of those squares to be white, and we can randomly assign 50% of those squares to be red. So that are the rules. So now let's do one round of that. So let's randomly assign 40% to be blue, and then let's randomly assign 50% of those to be red. And then, so that's one round. And if we would do many rounds of that, then on average, we would expect to see a result like this. Namely, we would expect that 2 out of those 10 squares would be both blue and red. And that's because 50% of 40% is 20%, and 20% of 10 is 2. And the same kind of logic applies to our features here. So if you multiply 15% with 15% and add them with 549, then we get the result that there are 12.4 passengers. So out of those 549 non-survivors, we would expect that on average there are 12.4 passengers that are both female and travel in first class. So now let's see how good this estimation actually is. Namely, because we are currently looking only at 2 features, we can actually look up in our training data how many of those are female and travel in the first class. So let's do that. And here then we can see that there are only 3. So our estimate here is not quite right, but it's also not that far off. So let's now do the same thing for those 342 survivors. So here we then multiply 68% with 40% with 342, and then we get the result that there are 93 passengers, and this is actually quite close to the actual number. So overall, if you look at the percentages here, then you can see that they are not quite the same. However, this change is not, this difference is not really a problem, because we are not really interested in the concrete numbers, but we are more interested in the general tendency. So for example, for a given specific combination of values, we are more interested in the fact if generally speaking more people survived or if more people died. And if you compare the percentages of this lookup approach here and this estimation approach, which is essentially the naive Bayes approach, then we can see that those percentages here are somewhat similar. At the very minimum, they both tell us that for the combination of values from test passenger 3, generally speaking, much more people survive. And that's what we're interested in for making our prediction. So then obviously in this case, we would predict that this passenger here survived. So let's see if that's really the case. And indeed, this passenger did survive. So our prediction here was correct. And with that now, we basically know how the naive Bayes algorithm works. And therefore we could go back to Bayes' theorem and check if we've actually done the calculations according to the formula. However, for the sake of completeness, let's check what our estimations are when we actually consider all the features again. So, and here, as you may remember, this lookup approach didn't work anymore. So there we had 0 examples in our data, in our train data for the combination of values from test passenger 3. So now let's see what we will predict with our estimation approach. So here is the calculation, and I've actually not created the whole table for that. I just wrote down the respective probabilities. And here, as you can see, our estimates are pretty small, and that's because we have to multiply together a bunch of probabilities. But looking at the percentages, we are now again pretty sure that this passenger here survived, which would be the correct prediction. So now let's do the same thing here for test passenger 4. And for that, again, we had 0 examples in our actual train data. So this lookup approach didn't work. And here, based on our estimation, we see that there is a 86% chance that this passenger here did not survive. So that would be our prediction. So let's see if that's the case. And again, this prediction was correct. So now let's look at also at test passenger 1. So here the lookup approach still worked. And if you look here at our estimations, those percentages are again pretty close to the actual number. So again, here we would predict that this passenger did not survive, which would be the correct prediction. And then lastly, test passenger 2, for which we also had examples in our train data. Here the percentages are somewhat different, but again, we're not really interested in the concrete numbers, but more in the general tendency. And in both cases, we are pretty sure that the passenger survived. So that would be our prediction. And again, this would be the correct prediction. So now we have predicted all of our passengers here, and all of those predictions were correct. So you might get the impression that naive Bayes always makes the correct predictions, but this is obviously not the case. That's just because I specifically picked those passengers here from the test set. So if we would then apply our naive Bayes algorithm to the whole test set with some small adjustments that we're going to cover in the next video, then we actually get an overall accuracy of 77%. So we would predict 77% of all the passengers in our test data correctly. And with that now, we have a basic or an intuitive understanding of how naive Bayes works. So let's now get back to Bayes' theorem and check if we've actually done those calculations here according to the formula of Bayes' theorem. And therefore, for the sake of simplicity, let's just again just consider the two features, sex and passenger class. Okay, so now let's look again at the formula for Bayes' theorem. So this is what it looked like, and so this is the general form, and we need this formula to calculate those respective probabilities here. So let's now use it to calculate the probability that given we have the combinations of values from test passenger 3, what is the probability that that passenger did not survive? So what we want to know is the probability that the passenger that survived equals 0, given that the sex is female and the passenger class is 1. And since this expression here is somewhat lengthy, let's replace these descriptions here with some shorter symbols. Namely, we're going to use an S with a subscript of 0. So this means that survived is 0. Then we're going to use this Venus symbol here to represent that the passenger is female. And then here this first represents that the passenger traveled in the first class. So now let's use those symbols and apply it to Bayes' theorem here. So we're going to start with the numerator. So there we simply have to switch things around. So here then we want the probability that the passenger is female and travels in first class, given that the passenger did not survive, and that we multiply with the probability that the passenger did not survive. Then here, the denominator, the first expression is the same, so we can just copy that. And then for the remaining expressions in the denominator, we need to look at the other, or we need to consider the other classes. So this is then simply where the passenger did survive. So this is what the formula looks like. However, we can't make use of this formula in this specific form, and that's because of those conditional probabilities here. Namely, here for this probability, conditional probability, what we want to know is, given that the passenger did not survive, so we are only looking at the non-survivors, we want to know how many are there that are female and travel in the first class. And in this case, since we are only considering 2 features, this is actually not a problem. But again, if we would consider all those features, then the number of possible combinations again grows exponentially, and we simply probably wouldn't have any examples of that specific combination in our training data. So what it means is then that this probability here would be 0, as well as those other conditional probabilities. So therefore then the whole term would be 0. So the probability that we get would be 0, and the same thing for the survived column here. So then we would have again just 2 zeros, and we couldn't make a prediction. So what we now need to do is we need to get rid of this AND operator here, and therefore we can make use of the multiplication rule for independent events. And what it means that events are independent, we will cover in the next video. For now, it's just it's enough to know that we need to use this formula. So what we can do is to calculate the probability that event A and B happens. We can simply calculate that by multiplying the probability of A with the probability of B. So this is now the general form. So let's apply it again to our use case here. So to calculate the probability that the passenger is female and travels in first class, we would simply multiply the probability that the passenger is female with the probability that a passenger travels in first class. So that's what the formula looks like if we apply to our use case. But obviously here we have conditional probabilities and not just regular probabilities. So how does this multiplication rule work in that case? And actually this is pretty straightforward. Namely, what we want to do here in this expression is we want to know what's the probability that a passenger is female and travels in first class. And therefore we simply multiply the probability that a passenger is female with the probability that the passenger is traveling in first class. And here what we want to do here is we simply want to consider non-survivors. So therefore then we simply multiply the probability that a non-survivor is female with the probability that a non-survivor travels in the first class. So this is how we can get rid of this AND operator here. So if we do that, then the formula looks like this, and this is now a formula that we can work with, because here we won't have the problem that those conditional probabilities are 0, because we are, so to say, now again considering the features here individually instead of looking at them all at once. So now that we have our final formula, let's put in the actual numbers into this formula. And therefore, let's create first some space. So now let's put in the values, and here this first expression here is the probability that the passenger is female given that the passenger did not survive. So we're only looking at non-survivors, and we want to know how many of those are female. So that's then here this 15%. Then here the next expression is the probability that the passenger traveled in first class given that the passenger did not survive. So that's, we're only again looking at the non-survivors, and here how many of those traveled in first class. So that's also 15%. And then lastly, we want the probability that the passenger did not survive. So that's simply the number of non-survivors divided by the total number of passengers. And this probability we actually write down as a fraction. And then the next, here on the denominator, these expressions here are the same, so we can simply copy those values. And then here, these expressions are simply then the probabilities for the survivors. So then we multiply the 68% with 40% with this 342 divided by 891. So now, before we actually calculate to calculate this equation here, we're gonna rearrange it a little bit. Namely, the first thing that we do is we bring down the numerators here in front of the fraction, and then we put everything that is not a fraction into the parentheses. And then in the next steps, we simply calculate what's in the parentheses. And now the calculation almost looks like that, what we've done here. So we only now need to get rid of the 1/891. So therefore, we simply factor it out here in the denominator. And now this cancels out. And then, as you can see here, we've actually done the exact calculation that we've done here. So 12.4 divided by 105.4. And therefore, then we get also the result that there is a chance of 12%. So given that the passenger is female in first class, the probability that the passenger did not survive is 12%, which is what we got here in our calculations. So as you can see, what we did here is exactly what we have to do according to Bayes' theorem. And with that now, we have reached the end of this video. And in the next video, we're going to cover some more additional points about naive Bayes. So thanks for watching, and hopefully I will see you in the next video.